This building is designed to move nearly 3 feet sideways and still stand, not despite the earthquake. Because of it, if a skyscraper doesn't bend, it breaks. Stick around, because by the end of this video you'll know exactly why the world's tallest buildings are built to sway, wobble, and even crack on purpose, and how that keeps thousands of people alive when the ground starts shaking. Before we get into it, hit subscribe and turn on notifications so you don't miss the next one. Now let's get into how these giants actually survive. The problem with tall and rigid. Early engineers assumed strength meant stiffness. Build it thick, build it solid, and it won't move. Earthquakes prove that idea deadly. A rigid structure resists ground motion instead of absorbing it, and that resistance builds up stress in the frame until something gives, usually the joints or the foundation. In 2026, engineers describe this as fighting the earthquake instead of dancing with it. The buildings that fought back are mostly the ones that collapsed in past disasters like Mexico City in 1985 and Kobe in 1995. Why sway is the point. Modern skyscrapers are engineered to flex. When seismic waves hit the base, the building sways, dissipating energy through controlled movement rather than letting it concentrate at one breaking point. Think of a tree in a storm. A thick, stiff oak branch snaps. A flexible palm tree bends almost to the ground and springs back. Skyscrapers borrow that same logic. The Taipei 101 tower can shift almost a meter at its peak during a strong quake and return to center without structural damage. The Tune Mass Damper. One of the most visible tricks is the Tune Mass Damper, a massive pendulum suspended near the top of the building. Taipei 101 uses a 660-ton steel sphere hanging from cables like a giant wrecking ball in reverse. When the building starts swaying one direction, the damper swings the opposite way, canceling out the motion. It's essentially a shock absorber the size of a house. Since 2026, similar damper systems have been installed or upgraded in supertall towers across Tokyo, Manila, and San Francisco as retrofitting old skyscrapers for seismic safety becomes a global priority. Base isolation. Some buildings don't just flex above the ground, they float above it. Base isolation involves placing the entire structure on rubber and steel bearings, or sometimes ball bearings and sliding plates that separate the building from the earth itself. When the ground shakes violently, the isolators absorb most of that motion before it ever reaches the structure. San Francisco City Hall and Los Angeles City Hall both use base isolation, and Japan has thousands of base-isolated buildings, more than any other country on Earth, because they treat this as standard practice rather than a luxury upgrade. Flexible foundations and deep piles beneath the visible structure. Engineers also design foundations that work with the soil rather than against it. Deep piles driven into bedrock anchor a building while still allowing a controlled degree of movement. Soft or loose soil can amplify shaking, so soil testing now plays as big a role in seismic design as the materials used in the frame itself. Getting this wrong was part of why buildings on loose sediment collapsed even when nearby structures on solid rock survived the same quake. Materials that bend without breaking. Steel is the backbone of earthquake-resistant skyscrapers because it can flex and absorb energy without fracturing, unlike unreinforced concrete or masonry, which tend to crack and crumble under stress. Reinforced concrete, when properly designed with steel rebar woven through it, gains similar flexibility. Newer builds are experimenting with engineered materials like shape memory alloys, metals that can bend dramatically under stress and then return to their original form, sometimes called self-healing structural elements. These are still mostly in testing phases as of 2026, but they represent where seismic engineering is heading next. The shear wall and outrigger system. Tall buildings also rely on shear walls, reinforced concrete or steel panels running vertically to the core of the structure, which resist the twisting and lateral forces earthquakes generate. Outrigger systems connect the central core to the outer columns like the spokes of a wheel, spreading seismic forces across the entire building, instead of letting them concentrate in one section. This is part of why modern supertall towers can be both taller and safer than their shorter predecessors from decades ago. Real-world proof. These systems aren't just theory. During the 2011 Tohoku earthquake in Japan, skyscrapers in Tokyo swayed dramatically, some visibly moving meters at their peaks, Yet very few suffered serious structural damage, largely due to damping systems and flexible design. Compare that to older, more rigid structures nearby that suffered far more damage despite experiencing similar shaking. The data consistently shows that flexibility, not brute strength, is what keeps people alive. What's changing now? As of 2026, seismic retrofitting has become a major focus in cities like Los Angeles, Seattle, and Istanbul, where aging skyscrapers built before modern codes are being upgraded with dampers and base isolation rather than torn down. Building codes and seismic zones are also increasingly requiring performance-based design, meaning engineers must prove a building will remain functional after a major quake, not just avoid collapsing. That shift alone is reshaping how skyscrapers are designed from the ground up. So the next time you see a skyscraper standing tall in an earthquake zone, remember it's not winning by being unbreakable. It's winning by knowing exactly how to move. If you found this as fascinating as I did, let me know in the comments which building's design surprised you the most, and subscribe for more videos breaking down the engineering that keeps our world standing.